Hi, I am Nitisaran. Here we are going to explain about process concepts in operating system. Contents. First, introduction to processes. Second, process scheduling. Third, scheduling criteria. Fourth, types of scheduling. Fifth, process synchronization. Sixth, inter-process communication (IPC). Seventh, deadlocks. Eighth, process management in OS. Introduction to processes. In an operating system, a process is a program that is being executed. During its execution, a process goes through different states. Understanding these states helps us see how the operating system manages processes, ensuring that the computer runs efficiently. Please refer process in operating system to understand more details about processes. Each process goes through several stages throughout its life cycle. In this article, we discuss different stages of process in detail. Definition and importance. What is processes? A process is a program in execution encompassing the program code, its current activity and the resources allocated to it by the operating system. Importance of processes in OS. Processes are essential for multitasking in an operating system as they allow the OS to efficiently manage and execute multiple programs by allocating resources appropriately. Importance of processes in OS. Processes are essential for multitasking in an operating system as they allow the OS to efficiently manage and execute multiple programs by allocating resources appropriately. Processes life cycle. New to terminated. The process life cycle includes stages a process undergoes from criteria. New through execution to termination, ensuring systematic resources allocation and delocation. Stages of process. A process can be various stages: new, ready, running, waiting, and terminated, each representing a specific phase in its execution and transition within the system. Process control block. A process control block contains key information about the process, including its state, program counter, CPU register, memory limits, and I/O status. Next, process scheduling. Process scheduling. The objective of multiprogramming is to have some process running at all times so as maximize CPU utilization. Next, third, scheduling criteria. Throughput. Explanation. Throughput refers to the number of processes that complete their execution per unit of time. Higher throughput signifies efficient scheduling. Turnaround time. Explanation. Turnaround time in the total time taken from the submission of a process to its completion. It includes all type of delays. Next, fourth type, types of scheduling. Preemptive versus non-preemptive. Preemptive scheduling. Preemptive scheduling allows a process to interrupt and replaced by another processes, ensuring crucial tasks are attended to promptly. Non-preemptive scheduling. Non-preemptive scheduling means a process runs to completion without being interrupted. Generally simpler but might lead to longer waiting times for urgent tasks. Long-term, short-term, medium-term. Long-term scheduling. Long-term scheduling determines which processes are admitted to the system for processing, controlling the degree of multi-programming. Short-term scheduling. Short-term scheduling decides which of the available processes which will execute text, focusing on immediate CPU allocation. Medium-term scheduling. Medium-term scheduling temporarily removes processes from main memory and places them in secondary storage, balancing the workload by swapping processes in and out. Next, fifth type, process synchronization. It has critical section problems. Definition: the critical section problems involves ensuring that multiple processes or threads do not access their shared resources simultaneously, causing data inconsistency. Requirements: to solve the critical section problem, requirements include mutual exclusion, progress, and bounded waiting to ensure proper access to shared resources. Solutions such as Peterson's algorithm and synchronization mechanisms like semaphore can be used to manage access to critical section effectively. Synchronization mechanisms. Locks are synchronization primitives that prevent more than one thread from accessing a critical section of code at the same time, ensuring mutual exclusion. Semaphores are signaling mechanisms that can manage resources sharing among multiple processes using wait and signal operation to ensure synchronized access. Monitors are high-level synchronization constructs that encapsulates shared variables, providing synchronized access through procedures and condition variables. Sixth type, inter-process communication. Mechanisms for IPC. Message passing allows process to communicate and synchronize their actions by exchanging messages. It is useful in distributed environment. Shared memory is a memory segment that can be accessed by multiple processes, providing a fast way to share data. All through it requires synchronization mechanisms. IPC synchronization. Blocking versus non-blocking. Blocking operation make a process wait until a event occurs, while non-blocking operation allows a process to proceed without waiting, improving efficiency. Buffering helps in handling communication between processes by storing data temporarily and can be implemented in different ways, including zero bounded and unbounded capacities. Seventh type, deadlocks characterization. Necessary condition. 4 conditions must be met for a deadlock to accumulate, exclusion, hold and wait, no preemptive and circular wait. Resources allocation graph. A directed graph used to represent the allocation of resources and can help in identify potential deadlocks. Deadlock handling strategies. Deadlock prevention. Strategies that ensure at last one of the necessary conditions for deadlock cannot hold, thereby preventing deadlocks. Deadlocks avoidance. Techniques like the banker's algorithm that plan ahead to avoid deadlocks by ensuring resources allocation in safe. Deadlock detection. Mechanisms to periodically check for deadlocks in a system and to identify the processes involved in a deadlock. Deadlock recovery. Methods to recover from deadlocks including process termination or resources preemptive to break the deadlock cycle. Eighth type, process management in OS. Modern operating system case studies. Linux case studies often focus on Ubuntu for user-friendly desktops, CentOS for servers, and Android for mobile systems, showcasing versatility and scalability. Windows case studies highlight Windows 10 for enterprise productivity, Windows Server for robust server management, and Windows 11 for modernized user experience. Comparison of process management techniques. Efficiency. Multitasking maximizing responsiveness by task switching, while multiprocessing boosts performance through parallel execution. Scalability. Multiprocessing scales better with additional CPUs, while multitasking relies on efficient task switching within a single CPU. Security. Processing often better security through process isolate, while multitasking saves resources, increasing vulnerability. Thanks.